So hello everyone, in this video we will proceed with our material and we will talk about the electrochemical classification of redox couples. We talked about, the last video was about the SHE, the standard hydrogen electrode. We'll complete with the material. And as a brief introduction, we've mentioned that we need a reference to calculate the reduction potential of every metal, and the reference here will be SHE, the standard hydrogen electrode. Our reference will be. So in order to calculate the reduction potential of any metal, we will assume that the SHE is equals to 0, the reduction potential of the hydrogen half cell is equals to 0, and we have other conditions for the hydrogen half cell. The concentration of hydrogen H plus ions should be 1 mole per liter, and the pressure of the hydrogen gas should be 1 bar. In the standard metal, for the metal half cell, the concentration of the metal, let's say Zn2 plus or Cu2 plus or Ag plus, should be 1 mole per liter. The pressure of the room should be 1 bar, and the temperature of the room should be 25 degrees Celsius. In order to make the standard conditions, we should have the concentration 1 mole per liter, the pressure 1 bar, and the temperature is equals to 25 degrees Celsius. Now, and we concluded that in order to calculate the reduction potential, we need the SHE, we need to take it as a reference. And we will assume that the SHE, the standard hydrogen electrode, to be the reduction potential of the standard hydrogen electrode to be equals to 0. Now, in this video, we will elaborate on this idea, and we will talk about the reduction potential of each metal, and we will classify the reduction potential of the metals that we will talk about according to the potential axis, reduction potential axis. So first, we will start with the first galvanic cell. As I told you, we need to calculate the reduction potential of copper. So we will associate the copper with the hydrogen half cell. We'll associate the copper half cell with the hydrogen half cell. And for this reason, we have the galvanic cell here. We have the hydrogen half cell and the copper half cell. Now, in order to figure out, or in order to predict which is cathode and which is anode, we can predict through the electron flow. The electron flow flows from the anode to the cathode, but we can do it another way. What's the way? So this is the electrochemical axis. If you still remember the electrochemical axis, this direction, the oxidation power increases, and in this direction the reduction power increases. Okay, so here we have the spontaneous reaction. To get a spontaneous reaction, the oxidation, the more oxidizing power should react with the more reducing power. So here we have Cu and H plus. So sorry, the copper and hydrogen. So here we have Cu has more oxidizing power than H plus. So Cu2 plus will react with hydrogen to give us H plus with Cu. So the reaction is Cu2 plus H2 is giving us H plus Cu. I predicted that through the spontaneity of the reaction. Okay, so here in this case, the Cu2 plus is undergoing reduction, right? You get Cu, this is reduction, and here the H2 is undergoing oxidation. Not red, I mean reduction here, reduction, not red, oxidation. Okay, and then the Cu here is gaining electrons, the hydrogen is losing electrons, so hydrogen is the anode. Okay, and here the Cu is the cathode, where reduction takes place. The Cu2 plus is being reduced, while the copper, where reduction takes place, the electrode where reduction takes place. So here we have the anode, here we have the cathode, right? Now if I want to calculate the reduction potential of Cu, E is equals to V for Cu minus V for H2. Okay, as you can notice that here we have, it's important that cathode minus anode. The cathode is the Cu strip, the anode is the hydrogen half cell. Okay, here we have E is equals to VCu. Here we assume that the hydrogen half cell is equals to 0 because it's as our reference. So VCu is equals to 0.337 volt. And we talked about the last video that VCu is designated by E node Cu2 plus Cu is equals to 0.337 volt. Okay, this is E node 1 is being associated to hydrogen half cell. Good. Let's have another example, which is when Zn, we link it with the hydrogen half cell. Okay, so zinc is linked with the hydrogen half cell. As you may notice that the spontaneity here of the reaction should be H plus is giving F, H plus Zn is giving Zn2 plus H2. You can see it here. So we have zinc plus hydrogen, 2 hydrogen, is giving us Zn2 plus H2. So I'm trying to say that from the electrochemical axis we can predict how the reaction is spontaneous, and we can from the prediction of reaction, if spontaneous or not, we can predict if which is the anode and which is the cathode in our cell. So here the H plus is reacting with Zn because this is how the spontaneous reaction goes. H plus Zn is giving Zn2 plus with H2. This is the overall redox reaction, and this is the oxidation of reaction. Zn is undergoing oxidation. Here the hydrogen half cell is undergoing reduction. So here we have, here's the cathode. Okay, SHE cathode, and here we have the Zn zinc anode. Okay. Sorry, and as you may notice that the electrons travel from the anode to the cathode. But I'm not concerned about that. I'm concerned about calculating the reduction potential of zinc. So E, okay, is equals to V for the hydrogen minus V for the Zn. Right? E is equals to 0.76. Here we have the hydrogen is the cathode minus the Zn, which is the anode. VH2, here we have H2 is equals to 0, so I'm going to cancel it. So here 0.76 is equals minus to VZN, so VZN is equals to minus 0.76. And here E0, Zn2 plus Zn is equals to minus 0.76. We're good? Done. Let's proceed again. Here we have another example. Hydrogen is associated with Ag plus with this silver. As you may notice that the reaction is spontaneous when silver reacts with Ag plus, reacts with H2 to give us H plus Ag. Here's the overall redox reaction. 2Ag plus H2 is giving us 2H plus 2Ag. So here the H is being oxidized, H2 is being oxidized, H2 is undergoing oxidation, and here the Ag plus is undergoing reduction. So here we have the cathode, okay, because the cathode is where reduction takes place, which is in the Ag electrode, and here we have the anode electrode, which is the SHE electrode, okay, and the electron flows from the anode to the cathode. Again, I'm concerned about calculating the reduction potential of Ag, and in this case E is equals to 0.80 volt. You can see this from the voltmeter. Okay, I'm calculating it through the voltmeter. E, which is equivalent to the potential difference, UPN. We talked about it. You can refer that to the first to the video of galvanic cell to know about more about E. Okay. So we have E is equals to 0.8 volt, and E is equals to V for the cathode minus V for the anode. Here the cathode is Ag, so E is equals to VAG minus V of H2, or let's say VSHE. It's a better terminology here. Okay, we're gonna name it VSHE. The electrode is SHE. We call the electrode as SHE. Okay, so here we have E equals to VAG minus VSHE. Then E is equals to, because this is equals to 0, then E is equals to VAG, and VAG is equals to 0.8 volt, which means that E for Ag plus Ag is equals to 0.8. Now I have to put all these in the form of axes. We got all these results. We have 0.34 for Cu for the copper redox couple. We have for the zinc redox couple minus 0.76, and for the Ag plus Ag redox couple 0.80. Now I want to put all these into a electrochemical axis. And here we have the increasing of E node. As you mentioned, as you notice that H plus H2 is our reference, so here it's 0. Above it we have the Cu2 plus, Cu, it's 0.34, right? And Ag plus Ag, it is 0.8, and below it we have the Zn2 plus Zn, which is minus 0.76. Now here we have an exercise. If you still remember Daniel cell, we calculated the potential difference. If we want to calculate the potential difference for Daniel cell, it's equals to V for Cu, which is the copper, which is the cathode, minus V for Zn, which is the anode. Here we have the V for Cu is equals to 0.34 minus that for the zinc, which is minus 0.76. This gives us 1.1, I think, right? Yeah, it's 1.1, which is the result of the Daniel cell. If you still remember that the Daniel cell, the voltage, the potential difference E is equals to 1.1. So it's verified. So that's how we calculate how from the reduction potential of each redox couple we are able to calculate the potential difference of the galvanic cell. Okay. So the classification of redox couples with regard, so we classify this redox couple with comparing it to the, or we have the reference, which is the hydrogen couple compound, and it's based on the reduction potentials, and it can be applied to all redox couples. Yeah, we have this. Here we have only 1, 2, 3 metals, but we can add. We can just, all we have to do is to associate the metal to the hydrogen half cell, and that's it. We're done, and we calculated the E. We have the E through the voltmeter. And we can calculate the reduction potential by assuming what? By assuming that the hydrogen couple is equals to 0. The SHE is equals to 0. Now here I want to talk about this idea, that the larger EM has the stronger oxidizing agent, and the smaller E, which is the reduction potential, has the stronger reducing agent. As you can see that as we rise, okay, we have a stronger oxidizing power. Oxidizing power increases. So if you want to compare this axis to the previous one concerning the oxidizing power, the electrochemical classifications, it's the same. AgCu H plus and Zn below H plus, it's the same. So as the E node increases, the oxidizing power increases, and as E node decreases, the reducing power increases. It's the same as the electrochemical axis. Okay? And here we have the stronger reducing agent. So if I want to predict the spontaneous reaction, the one that has highest E node should donate the oxidizing power, the oxidizing agent. And the one that has stronger, lower electrochemical reduction potential should donate the reducing power. For example, let's have an example of, let's say I have the E node. I gave you the E node of Ag plus Ag is equals to 0.8. And that for the Zn, we know it, Zn2 plus, we know it, it's minus 0.76. So which one has the highest oxidizing agent, reduction potential? Is 0.8. Because it has the highest reduction potential in the reaction to be spontaneous, it should has the highest oxidizing power or oxidizing agent. So here the Ag must react with, if we have the lowest, here we have the lowest reduction potential, the reducing agent should react. The stronger reducing agent, the lowest, the smaller E, the stronger reducing agent is. So here it should react with Zn to give us E2Ag plus, to give us Zn2 plus Ag. 2Ag. Okay? And if it's the vice versa, it will not be spontaneous. This is the spontaneous reaction. So if we go to check with the gamma rule, yes, Ag plus should react with Zn to give us Zn2 plus Ag. So as you may notice that through the reduction potentials, I can predict which reaction is spontaneous between the couples. The one that has the highest should donate the oxidizing agent, and the one that has the lowest should donate the reducing agent. Okay? The last idea is, okay, how the reaction is spontaneous. A spontaneous reaction takes place between the stronger oxidizing agent, which has the more positive E node, with the stronger reducing agent, which has the most negative E node. Okay, hope that it's clear now. I want to talk about the continuity of the reaction. Complete. How can we say that the reaction is complete or not? One, delta E node is above 0.3 volt. So let's say we have in our case we have E node Ag plus Ag is equals to 0.8, and we have the E node for Zn2 plus Zn is equals to, let's say, minus 0.76. We calculated it's minus 0.76. And we said that the reaction, if you still remember, 2Ag plus, this is the spontaneous reaction, plus Zn, okay, is giving us 2Ag plus Zn2 plus. Right? And here the 2Ag plus 2 electrons is giving what? Is giving Ag, 2Ag. Here we have a reduction. And the oxidation is, when we have Zn, is giving Zn2 plus 2 electrons. Right? Here we have the oxidation, and here we have reduction. Here also the reduction occurs cathode. Here we have the anode. So if I want to calculate the potential difference, the delta E, okay, V for Cu minus, cathode minus V for the anode is equals to, who's the cathode? The Ag. Ag has the value of 0.8 minus, here we have minus 0.76, which is the Zn here in our case is the anode because it's undergoing oxidation. This means that it's equals to 1.56 volt. Here's delta E is equals to 1.56 volt. 1.56 volt is not definitely more than 0.3. So 1.56 volt is more than 0.3. In this case, we can say that the reaction is what is complete. So the reaction is complete when the delta E is above 0.3. So the reaction between the zinc Zn and the ions of Hg plus can also be predicted also by the gamma rule, if it's spontaneous or not. We can go back to the gamma rule, okay, and we can predict if it's spontaneous or not. Or we can predict it through the the reduction potentials that's given, if it's spontaneous or not. And we can say if it's complete or not if the delta E is above 0.3. Okay, this video actually it's short. Hope that you enjoyed the video and you understand more what does reduction potential means and how we can apply it. By calculating the reduction potential of each metal, now we can predict and we can calculate the potential difference of each galvanic cell. Hope that you enjoyed the video and see you later.